And thanks for coming. I won't repeat since Ron already stole my subtitle there. So, and as Ron said, this is kind of a continuation of that last non-travel talk Rocky gave. And it's kind of, here's what some things maybe you need to think about when you're read some articles or see some numbers and what they really mean. So, all right, so what is statistics? It's, here it says science, but it's sort of a science of collecting and analyzing data. An important part is it's a law of large numbers. You need a large data set if the numbers you make up are actually going to mean anything. I think the important thing about statistics is it provides a generally accepted framework so people can do consistent comparisons. And I guess an important thing is statistics don't exist in nature. Everything is its own thing. We, as humans, and as Rocky said, we like to put things in categories, sort things, see linear relationships. And then, and although it's being hidden, statistics don't exist in nature. That upper photo, the upper plot shows, those points and facial recognition. Those things all work on a statistical analysis. And what they do is they don't do an exact match, but they'll do a good enough match. And that's one of the things in statistics is what is good enough. Same way with your iPhone, with your thumbprint, that's some statistical analysis. Oh, I got to hide it, don't I? I was waiting for Ron to do it. And then there's just one little thing. Oh, wasn't it working again? Okay, so the thumbprint you use on the phone, that's all statistical analysis. And these two kind of things are statistical learning techniques, which is Bayesian statistics, which I'm not really going to talk about because that's not what this talk is about. That would just getting in the basic of Bayesians would take a long time. Down. All right, just gonna go. There we go. All right, so here's a headline that said shark attacks up 43%. So you can see consistent with long-term trends, they're seeing more shark attacks. Let's say 42% higher. And at this point, 42% higher means there were just a few more attacks. 42%, that could mean there were thousands more attacks or 5 attacks. If you don't know the basis for that percentage, you really don't know what it's implying. As the bottom one says, odds for dying from a shark attack are a whole lot less than dying in your car by, a couple 100,000 times. And there's some other questions you would want to ask yourself about this. It says that the 47 cases of shark attacks in the US accounted for 64% of the world's total. Now, I find that not a real believable number. You look at the rest of the world, majority of the population lives close to a coast or on the coast, work in water, all that sort of thing. So does that mean sharks only like attacking people off the North American continent? I don't think so. So, it's okay. So who reports? Well, I guess we report because shark attacks are something exciting, even though it's an extremely rare event. So most statistics have that kind of background to them. You can't trust them unless you know what the actual basis is and if the data is true or not, or viable, variable. So here, this is from Google Statistics. So we look at a shark attack correlation. As Rocky talked, people like straight lines. So here we have that R squared value, which is this one, R squared 0.92 something, says this is almost a straight line relationship. So that's something people like to look to. But I left the y-axis question marks. Anybody have any guesses on what that might be? That gives that good relationship? I'll tell you. It's the, what did they say it exactly? It's ice cream sales. So if you look at Google Statistics, and they got lots of statistics, you can get a real good relationship between ice cream sales and shark attacks. So the question is, does it mean anything? And correlation does not mean causation. And that's a lot of statistics seem like they draw fallacious causation results. Okay, this is another one of Rocky's favorite things, and it's the scale at which you display data is very important. So this data was the removal of 400,000 gallons of high-level radioactive waste from 4 1.3 million gallon waste tanks in southeastern Washington at the Hanford site. The green line shows the risk before the waste was removed. And then the red line, the waste after removal, the risk. And it shows got it down to about 75% of the original waste. So DOE claimed victory and said, we did a really good job getting rid of most of the nasty stuff in there. DOE sites are government-owned, contractor-operated. So the contractor who did the clean-out got tens of millions of dollars for doing that. The problem is, when you show the whole story, this top line up there, that's the that's what the EPA drinking water standard for a particular radionuclide they were looking at, which is technetium-99. It's 900 picocuries per liter, which is just a number. Well, yeah, those are the units of a radioactive concentration. So now we can see, compared to that limit, we started off with not a whole lot of risk. We were 17% of the risk-based limit, and we ended up at 3% of the risk-based limit. So the question is was that worth doing? Because, now you had, worker risk, all sorts of other kind of things that could have gone wrong. So the bottom line is to reduce the risk from not much anything to less than not much of anything costs over $120 million. So of your tax dollars. So, is that the kind of thing we should be spending our money on? Did we get much bang for our buck? And the answer is no. So we can go from a presentation from this scale where it looks like they did a whole lot of good work down to here, down to here where it didn't do anything to reduce the risk and it cost us a whole lot of money. Just as a little side point, that risk-based Tech 99 drinking water standard up at the top, that's another number derived statistically. And, so then you need to know what that means. Is it a 97th percentile number? Is it the LD 50-50, which is a lethal dose to 50% of the population, 50% of the time? Don't know that. So then it's, what is that limit? Although, that's so you could make an informed decision if you were one of the decision makers. But if you don't know the basis of that, that's again makes it more difficult to figure out what is going on. Just a common statistic, the mean or average, that's one we see thrown around all the time. A lot of times they're not very meaningful at all. And for some reason, statisticians like this unbiased mean, which is you add all your stuff together, divide it by the number of things minus one. I've never figured out the minus one, especially if you have a large data set, it becomes really meaningless, but that's the definition. And that's what statistics is. It's all defined quantities. Like I said, it has no relationship to nature. It just is something we've designed. And so if everybody uses this equation to calculate an unbiased mean, then we at least have sort of a common basis for comparing things. So let's look. We got a nice neighborhood. Got 9 houses that all cost $100,000, and then the developer stuck himself a nice big house in the middle for 1.1 million. So what would the mean be? So down at the bottom, it shows the mean would be 222,000. So it said, we're in this neighborhood, all the houses are an average price of over 200,000. So is that really reflective of what price you would find in a neighborhood? And it also shows the law of large numbers and why that's what statistics should apply to. Because if you take that unbiased mean with 10 samples, it makes a 10% difference, not surprisingly. So if it were, 1,000 homes at 100,000 and 10 homes at $1 million, you'd be a whole lot closer to the $200,000 average, which is what you would expect the average to be, rather than that extra 10% thrown on. So I think just in about every case, a median is a more valid statistic. It really tells you where things lie. And the median's the middle value of an ordered list. So in this case, we have an even number. So you can't find the middle value, but you compute the middle value by an average again. So there's some kind of iffy stuff about that. And so the median value of the home would be 100,000. And then statisticians like all sorts of different things to confuse things. So there's something called a geometric mean, which is used for things that maybe there's a large spread, and that's to kind of try to get away from this having one or several data points totally bias the final statistic. So if you do the geometric mean, and I guess what this means is instead of a sum, that's a multiply. So you multiply all 10 together, and then you take the nth root, which would be the 10th root of that, which That gives you 127,000. So that's still a whole lot closer to what you would expect the mean price to be rather than the unbiased mean, which was $100,000 higher than that. So, some of it depends on what statistic you see and how it's used, and it's not always clear. It's not always clear how it's presented. Somebody could just say the mean's 127,000, and you go, well, how'd you come up with that? Because that's not how I would expect a mean to show up. Okay, here's a bad thing. Extrapolating outside the data. So here we see, this is a shark attack thing. An extrapolation of the data means, okay, if I'm up here, if I got 40 shark attacks, what would be the how much ice cream would have been sold? And I'll show you why that can be a bad thing to do. There it is. Let's see, or is that down here somewhere? Whoa, what happened there? All right, I got to go to another screen here. That's there we go. Boom. And then here. All right, so this is going to show a titration. I don't know if you all are familiar with titrations, but it's a chemical technique. And it can be dramatic. So here we have, we'll skip all that stuff. Is that going? There we go. That's right here. Okay. So what she has is, I think sodium hydroxide or no, hydrochloric acid. And then, so she's putting this orange stuff in it. So he added some to get it started. And then, let's see, how far? Whoop, too far. So, and then here, the concentration of the orange stuff is getting greater and greater. And then we get near the end point. And here she does one drop, takes it up, and boom, it's something totally different. So if you were to just extrapolate the data for as far as you wanted to, and if you didn't have data of that last point, and that happens a lot of times, you don't have data that covers the full range, you have no idea what's coming. You might be able to infer from prior knowledge, have a guess as to what would happen, but nothing's for sure until you actually can prove it. And statistics is not a proof. It's just a guess at best. So let's see, then we need, control. There we go. Whoops. So this is something I saw happen. Whoa, not there. I need this. There, okay. So extrapolation outside the data is something I saw all the time when I was working. even with people who supposedly knew what they were doing, it was still a stretch. And really, until you prove or know what's out there, you can't really say definitively if something really will happen that way. And that's when we talk about the statistical learning, Bayesian statistics. Bayesian statistics uses priors to inform the afters. And what that still has the problem of if you have a step function or a discontinuity in your physical event, that's not something any sort of extrapolation or even a Bayesian analysis is going to pick up for you. So the independence of statistical events, that's one of the bases for classical statistics, is that each datum is considered to be independent. So that means it doesn't care what came before, doesn't care what comes after. I just always kind of like this. I don't know if y'all are familiar with it. This is an impact crater up just north of the Gaspé Peninsula. And that's about 20 miles across, a little more. So that was a big something that hit, or at least something with a whole lot of energy. And so the statistic you can find is an average of 1 in 500,000 years. So what that doesn't tell you is meteor strikes are independent events. So it could be the 500,000 years is an average. So for truly independent events that we don't know much, statistical entropy is at its greatest, which means any time within some defined interval is equally likely to occur. So you could have an event happen today, and the average is 500,000 years, but it could happen again today or tomorrow. So same thing here. We hear about all these weather events, and it's a 50-year storm. Well, we could have the 50-year storm every year for 10 years. You just got to think about what it is, what the time frame is. All right. So I had to really control myself because I have lots of issues with medical studies. So I only got 2 slides on it. One is this epidemiological kind of way of doing it. And I actually did do some work with the director of zoonotic and foodborne diseases at CDC, because I knew his brother who was Los Alamos. And so his brother and I had some consulting work we did for the director. So this is, I guess, the big problem with at least epidemiology, because my older son spent a few years working on a PhD in epidemiology, is they're still stuck in 20, 30, 40-year-old statistics, and mostly because of publications. And this is the kind of stuff they like to see in publications. So if you don't have these pictures, you're not going to get published. And that's all they really care about. So what they do is they'll run a study. And in this study, there were 2, 4, 6, 8 independent variables. So independent variables means those are things that can change however they want to, as opposed to the dependent variable, which is the data. And the data depends on the independent variables. It's a function of. So like I said, so they plot each variable against every other variable, and they come up with these scatter plots. And the reason they do this is they're looking for relationships, and they hope it's linear relationship, or if it's something more complicated, then they probably all ignore it. But let's see. This is something like this ignores causation and correlation, because they'll say, oh, this looks good. One of these things could turn out to be, like this one. You say, oh, that looks like a good linear fit. Whether the two axes have anything to do with each other, meaning whether the y-axis is dependent on the x-axis, you don't know. It may be, it may not be. If it doesn't, which, all right, what did it do here? Oh, somebody wants in. Do I need to do that, Ron, or do you? Yeah, it did. Okay. So, yeah. Well, they try to find these correlations. And back in the good old days, we called it statistical fishing, where somehow you put enough things in, you're going to get something that'll give you a nice looking relationship that'll get you published. Oh, had something. Okay. And then meta-analyses. These are the new big thing, mostly because people are cheap. And meta-analyses are real cheap to run, because basically all you do is plunder the literature and get the data. I saw one just recently that was some sort of medical one. I forget what it was, but it's headlines, meta-analysis with 120,000 participants and 1,000 labs with the various collections. So that, gave you all kinds of data, but what they don't tell you in those meta-analyses is they're not looking at the raw data. They're looking at the published data, which has been mushed around and cleaned up and who knows what. And part of the problem with that, or the big problem with that, is from 1,000 different studies, that means there could have been 1,000 different ways people cleaned up their data. And data is always cleaned up. I don't care what anybody says. So, you don't know what the consistency of all your data sets is, or if there is any consistency. And then what you end up with is you have all these conclusions from all these 1,000 papers, and then I'm going to take their conclusions, which are their statistics, and I'm going to mush their conclusions together and say if the statistic is a mean, what I end up doing is taking a mean of the means. So I'm taking averages, which may or may not be real reflective of the event, and then I'm going to throw all them together and take an average of them and spread them out some more. And I guess one of the things in medical studies is everybody lies. You ask somebody, how much have you drunk? Or how much do you drink a week? And I have a sip once in a while, not too often. Or how much sugar do you eat? Not much. So a lot of these analyses involving medical have a fudge factor for lying, which means they'll discount X amount of information. So they're trusting people to lie, but they're trying to decide how many people lie based on people who lie telling them they lie. It seems kind of a circular argument there to me. This one story, my younger son was involved in a diabetes study with a European guy. They were doing a diabetes study in Poland. And this was a long-term one, so they had to pay the guys to show up and get the blood tests, whatever. One guy came in, and the guy who was running the test was looking at his information and said, you know, this says you're 65, but you look about 20. I said, oh yeah, that's the subject's my uncle, but he told me to come in so I could get the money. So stuff like that. The other big thing with medical analyses, most of them are done at universities, which means most of their sample sizes, which are small, 20 to 50, are usually 18 to 22-year-old white males. So that real bias then in those results right there. And then underlying assumptions, this is kind of getting down into the weeds, but it's by picking a distribution, which all the statistics rely on, you're saying, I know something about the data. So if you don't know anything about the data and you're honest about it, you would use the uniform distribution, which is the one on the left. And what that says is every event's likely as any other. As soon as you go to something like the normal distribution, which most people are familiar with, that says you expect the data to trend toward the mean. Theoretically, you have a large enough data set to give you a significant, to give that significance. And it applies, you know, something about the underlying phenomenon, meaning I'm doing some analysis on some physical event. And to do my analysis, I'm going to use a standard deviation or a normal distribution. So right there, you're saying I'm going to have data that skews toward the mean, and it has a nice even distribution on either side of the mean. So, and there's probably about a dozen different distributions that are used. You got discrete, where things only occur at certain intervals. You know, there's a gamma where things are biased one side or the other, and there's a log normal distribution where instead of just being the values of the numbers, it's the log of the numbers, and that's one way you can start fudging stuff that's say orders of magnitude different. You know, you got 1 in 1,000 or 1,000,000 in the same data set. So how can I do those? And so there's all sorts of ways that they've come up with that we can do numbers. All right, here's a simple test for somebody who needs to give me an answer. So a car drives 1 mile at 60 miles per hour and the next mile at 30 miles per hour. So what's the average speed for 2 miles?
I think 45.
But you would. But
that's what pops in.
Because you just averaged the two numbers. The problem is it's miles per hour. So it takes you a minute at 60 miles an hour, 2 minutes at 30 miles an hour. So your denominator changes. So actually your average speed's 40. So that's the other thing. A lot of certainly popular literature and even in scientific literature, people ignore units. That's one thing in engineering. I like units. As my boss used to say, units are extra. But units are different. So unless you know exactly what it is you're doing, if you just saw numbers, a mile at 60 and a mile at 30, then 45 would be a good answer because you don't know any more information. But when you got the information, you have to make use of it. You can't ignore it. So that's pretty much it. I hope I gave you some things to think about. That's just, oh, it's going the wrong way. Yeah, that's it. Any questions? No?
So the
Oh, yeah.
big debate of the day is on climate change, all the statistics that are thrown out on that.
Right.
What's your take on?
My take is the climate always changes. It always has, it always will. We're still much cooler than we were a few 100 million years ago. In geological time frames, 100 million years isn't a whole lot of time. And certainly this time change or these temperature changes are occurring. They're occurring rapidly. The question is how much of it's the anthropomorphic effect, how much is man caused?
Yeah.
And that I think is where the debate lies, but people seem to ignore it. They just throw the natural cycle with the human component. And I think that's showing a lot of the human hubris. Because, sure, we can change anything we want to because we're so great. And it's just the scale at which climate change occurs. And then we don't really have good modeling for it either. It's, what they call mesoscale or megascale modeling for the atmosphere. So what computational, it's really fluid dynamics. If you look at how the atmosphere or the oceans mix, and then it's what size of the scale or the computational cells are you using? Because that's how you do it. You got to chunk things up. So now, I got a cell that's 100 kilometers by 100 kilometers by 100 kilometers. And that's the kind of scale you have to use if you're going to do a whole atmospheric model and you want to get results sometime within your lifetime. So within that big computational cell, now you're somehow averaging everything that comes in and everything that goes out. So now you're smearing things out. So the other problem with that is, you have stuff coming in, you have stuff going out. And so what happens in the middle? So say, okay, I'll do a centered value, and that's going to be my average of what goes in and what went out. But what that says then is, say it's 100 kilometers, that could take some time, but depending on what time scale your computation is, you could, the 100 kilometer computational cell says instantly what comes in, an average of it goes out. So how logical is that, or how reasonable is that? So that's why some things are going now. The new paradigm is multi-scale, multi-physics. Different things happen on different time frames, on different scales. The physics are different based on which scale you're using. And that's one way they're trying to get around the computational speed problem they have is if I can do big, huge computational cells over here and where something's really happening, I can do small cells, then I can advance my calculation much quicker than if they're all small cells. Well, I won't get in. That's what I used to do, and I could talk a lot about that. So, any other questions? Yes.
Friend went to a book study or something about the China study. And I was,
Oh,
this is about the China study.
oh, Yeah, turn it on. Turn it on. This one light up. You're on now.
Apparently they wrote a book about the China study.
What China study?
Oh, you haven't heard that one? Where I think it was back in the 90s. They allowed these people to go into several villages and they only had 5 days and they drew everybody's blood.
Mm.
And they're touting how healthy the Chinese are,
Uh-huh.
but they mixed everything together. The women,
Yeah,
the children, the adult, genders, nothing was separated. They just took all that because they were just drawing blood and getting it as fast as they could.
yeah.
Had you heard anything about that?
Not that, but based on, I'll say on my opinion is I don't believe anything that comes out of China. They steal a lot of data. They manufacture a lot of data because they've taken publish or perish to extremes. So anything,
And I know there's a book study or something going on now here. That's why I bring it up because I've read other articles in China, in the China study. And I just I never read it. So that's a disclaimer, but I did read that they had smashed all blood samples together. There was no differentiation between gender, between.
that's right. Yeah, the 10-year-olds are a
age.
whole lot more healthy than the 90-year-olds. Right?
Yes. Yeah.
So I think that gets back to Rocky's previous talk where it's, you got to ask questions about what these things mean or where they might come from. What's I going to say about this? Yeah.
As a research coordinator who worked really hard to make sure that the data was the way it was supposed to be, I'm now wondering if it doesn't matter. Someone is going to take the data
Absolutely.
and manipulate it to
Yep.
bring a new device or a drug to market.
Yeah, I guess.
But there are many people, many nurses, I'll say, who work really hard to make sure patients are selected appropriately, informed appropriately, and the follow-up is done carefully. And we do bring new drugs to market that are doing wonderful things for people or devices to market. But your talk brings up questions about how this could be manipulated.
Oh, yeah. Pretty much. Yeah.
Right.
If it's industry or academic, and kind of the old joke in engineering is, what do you want the answer to say? Because you can always probably come up with the right answer. And that's one way a lot of people, I never had the problem, but it was, they want to make their bosses happy. So I'll give an example. When I first got out of grad school, I was up at the Idaho National Lab. I was given this $30 million experiment to design. And so we were in code development, meaning we were designing a code that would predict, I never liked predict, a code that would infer how a nuclear reactor might react to a small break. And so I had my code, I came up with my results, and my boss didn't like the results. So he had me sit down with him and come up with these are reasons why it should come out the way we want it to come out. And so it's okay. I didn't know too much back then because I was fresh out of school. So this program we were on was an international program. As the experiment was running, if the data was streamed live in a conference room where all these international participants were, and you could just see my data went one way, or the data that was forced on me went one way, and the experimental data went another way. So that's how things get biased. I guess another, I think, big problem with research is they won't publish negative results or the null hypothesis. So another example of that, this was at the Savannah River site. We were running an in-tank experiment, meaning we had a 1.1 million gallon tank or 1.3 million gallon tank. Yeah, we were running an experiment and seeing how much benzene would get generated. But anyhow, the management had an expectation of how the experiment was going to turn out. And it turned out anything like their expectations. So according to management, the experiment was a failure. We got tons of really good data. So to all of us running the experiment or looking at the data, it was a great experiment. But management just, it was just a waste of a few tens of millions of dollars. And DOE money comes in a lot of big magnitudes, you know. A million's chump change. It's like that 120 million I got doubled away at Hanford for no risk reduction.
Statistics of an earthquake in California. The big one.
Oh, yeah.
It lives out there.
Yeah, I got one was right on the San Andreas fault, but
Yeah.
that could happen today. It could happen in 10,000 years. I mean, what about Yellowstone? All their when that goes, same thing. Theoretically, it could happen tomorrow or today. Or yeah, we were out in Idaho when St. Helens blew, and we got some of the dust, and that wasn't even a real big one in terms of volcanoes, but it made a mess. Yellowstone goes. I guess that's going to be a extinction level event, maybe. So we'll hope that's no time soon. That it? All right, Mark.
Yeah, a local example, now that all the city officials involved are no longer working in City Hall, is that the city manager at the time was very much into privatization and wanted to get rid of the Civic Center. So they ordered a study, but he knew one part of the study would tilt it towards keeping the Civic Center. So he said, well, we're not going to pay for that part of the study so that it'll come out how he wants to sell it. So you see that sort of thing is that there are multiple components to studies, and we'll just drop that out and not study what will go against us.
I wouldn't even say there are multiple components. They're slanted toward what result they want. That's why I like doing phone polls. I'll answer them, but then I always at the end ask them, who are you doing this for? Because a lot of times it's real obvious what their bias is. So yeah, they're good at
Drug studies are one of my favorites.
What are?
Pharmaceutical drugs, where the lawyers will say, well, your deadline was this date, so we're not going to count the people who died or had serious side effects after that date.
Well, yeah.
And not report those.
Yeah, that's what Bill was saying. Yeah, we don't like this data.
We rely on what's called aftermarket reporting, which a busy practitioner has no interest in doing. Ability.
Right.
Or the mechanism.
It's like a new model of car. You wait a few years for it to be experimented on others before you take that drug.
But in fairness, it's a big lumpy system. But we do develop new life-saving technologies and those.
Yeah.
We do tend to progress.
Yeah.
You know, the wheels fall off now and then, but we do tend to move forward.
Well, the whole thing is, and this is what the last 15 years of my career was what risk are you willing to accept? And the risk analysis. I guess that's one of the most famous, at least in engineering circles, risk analysis was Challenger disaster, where engineers said no, management said yeah,
Well, as individuals, we want no risk. As a large group, we have to be willing to accept some risk, as long as
We accept risk every time we drive the car. Or,
all right.
yep. Oh,
Well, the flu shot. They don't do clinical trials on flu shots. You are the clinical.
well, and plus, that's just a guess of which strain of flu is it gonna be.
Because how can you know?
Yep,
But people are willing to take that risk, so that's
yeah,
your statement, we want zero risk, but people are willing to take that risk because they're more afraid of the flu
Right.
than they are of
Right.
getting it and trying to recover.
People, more and more people now say, no, I won't take vaccine, even though we're starting to go backwards. Polio,
uh-huh,
tetanus, for God's sake.
yep,
Because people
That's
don't
a
want
big
to.
That's not a virus.
But it's, the whole vaccination issue has become fraught.
I think so.
Because of concern over.
Because they don't do the clinical trial. And you can make any clinical trial come on,
yeah,
whatever you want.
yep. You can say it was 100% effective if you had one guy.
Okay,
Yeah. That's, my younger son has developed a novel technique in epidemiology, basically, where instead of looking at these single things, he's looking at networks and he's looking at network of genes. And so they developed a treatment based on his analyses. This is getting into the kind of the personalized medicine stuff. And so they gave it to 4 patients, and 4 patients showed great improvement. But, you know, that was just 4 patients. Now, if that were done in a company environment, that would probably be headlines saying cured 100% of the patients. You know, and that's a problem. Then you get the marketing people involved. It's spin doctors and all that stuff.
Then half the cost of the drug is the marketing.
Oh, more. That's what I like. Or when you get drugs, you try to decide. So is the drug expensive or is the manufacturing expensive? Because, you know, you'll get, what is it? There's some things that, you know, maybe you'll be $1 a pill. And then the same pill size, but it's $1,000 a pill.
What you don't see is the millions of dollars spent on drugs that don't go to market because they failed in trials.
Well, that's, as I said, they never publish negative results.
So cost of drugs is a complicated issue.
Another thing is that makes it even more expensive because you probably have somebody else going down the same worthless path, running the same tests because you don't say this didn't work. And that's an important result, and it never gets out there. Now we could go into the whole social science thing, like or psychology, you know, where the leading guy in the world, they went through his data and found it was all, most of it was made up. And, you know, they got fired from his university in Sweden, I think, some European, and got his PhD stripped and all sorts of things because, you know, something like that, the studies aren't reproducible by definition.
And you wouldn't want your competitor to know what didn't work. You'd want him to waste his money on doing what you've already done. So when it's a commercial
Yeah,
venture, work against Lilly or whatever.
that's right. If you want to be the first out with the stuff that works.
No, I think it's, what do they call it, recommended daily allowances?
Oh, yeah.
Vitamins.
Oh.
Things, it's on mice. They do all these things on mice, like a mouse vitamin D,
Mm-hmm.
and then they'll come up with
when the mouse dies. Toxicity or something,
Yeah.
then they extrapolated
Hmm.
to a human being and average all that, that's all that is.
Yeah.
It's horrible.
And I always thought it's stupid, like, okay, a dose of Tylenol is 2. So am I a 100-pound woman or a 300-pound man? I still got to take the same dose?
It's
And
too complicated for Americans to calculate so many milligrams per kilogram. And label.
that's because they're not imperial units. That's the problem. They had ounces. But then is it liquid ounces or weight ounces?
They need to tell
Oh, yeah.
the biggest.
That's why this whole COVID testing and new vaccines is sad. Big pharma plot. And get conspiracy theories going now.
Kind of conspiracy here of really.
Oh, yeah. That it? Well, thank you all.